Hi there, welcome to Asina's Developer Channel. I am Mike Horton, CTO of Asina and your host. In today's video, we will talk about CAN bus and why CAN bus is an excellent interface for inertial measurement units on vehicle systems, and why a CAN bus based IMU can make autonomous and robotic vehicle systems safer. We will talk about how to develop inertial navigation applications with CAN bus using Asina's free open source tools and the Asina Open IMU 300RI hardware module. Now, let's take a second to refresh and talk about what an IMU and what CAN bus are. An IMU, or Inertial Measurement Unit, is a device that consists of 6 or more axes of motion measurement. There are 3 axes of linear acceleration in X, Y, and Z, and 3 axes of rotational rate, also about the X, Y, and Z axis. The 3 linear and 3 rotational components capture the fundamental Newtonian dynamics of whatever the IMU is attached to, including Earth's gravity and even Earth's rotational rate. An IMU may optionally include 3 axes of magnetic field sensing to measure the Earth's magnetic field and estimate direction or heading. CAN bus is a very mature standard for data communication that was born in the automotive industry over 30 years ago. It consists of a low-cost physical layer combined with a robust and reliable messaging transport protocol. As autonomous and robotic vehicles require many sensors to reliably exchange data, CAN is an excellent interface choice for low and medium speed vehicle sensors, such as the IMU. Asina makes 2 devices that implement the CAN bus standard. The first device is the MTilt 305D. This is a dynamic tilt sensor. It provides accurate dynamic roll and pitch, angular rate, and linear acceleration. It outputs this data over the CAN bus using the J1939 protocol. We will talk more about the J1939 standard in a moment. The second is the Open IMU 300RI, which is the open source sibling of the MTilt 305D. It has all the functionality of the MTilt 305D as well as a 3-axis magnetometer, and it fully supports the Open IMU open source stack for creating custom applications that live inside the Open IMU 300RI hardware. I'll spend the rest of this video discussing details of CAN bus and how one creates a custom application using CAN bus that runs on the Open IMU 300RI. Now, the CAN bus specification itself has 2 message standards for messages: CAN 2.0A with an 11-bit identifier and CAN 2.0B with a 29-bit identifier. Both work on the same physical layer. The physical layer has standard baud rates of 250 and 500 kilobits per second as well as 1 megabit per second. In my experience, you commonly see both the 11-bit IDs, for example in consumer automobiles, and you see 29-bit IDs, typically using the J1939 protocol in trucks and heavy equipment. So we will briefly discuss both message types and how to build applications with both message types using Open IMU 300RI. Now, before we get started coding, let's talk about debugging CAN applications, PCs and Macs that do not have a CAN port, so we need some external hardware. There are many options, and I'll show you 3 of them. The most developer-friendly is the PyCAN Shield for the Raspberry Pi 3. Asina, in fact, has some open source Python test code which uses this hardware, and we've posted that on GitHub. The PyCAN itself is only $50, and the Pi 3 based setup is super flexible with C and Python drivers available. Another option is to get an off-the-shelf USB CAN analyzer like the Komodo CAN Solo. This is a $300 option that works great for basic message logging. Finally, there is the gold standard of CAN analyzers, Vector. Vector tools are the standard in automotive and support debugging really complex scenarios, but the price tag is quite a bit higher to get into Vector tools. Now that we have some analyzer options, let's go ahead and build an IMU application. Since many automobiles use CAN 2.0A with 11-bit IDs, we will start with this case. CAN messages are available on a CAN over the OBD2 port, but this messaging is not globally standardized. To get a feel for what these messages look like, we can turn to the open source OpenDBC project, which declares its mission to democratize access to the decoder ring of your car. Now, a DBC file, and there are a bunch of them listed in this project, is just a file that describes all the messages from a device on the CAN bus. Here's an example message found on a 2017 Honda Odyssey taken from the OpenDBC project. A few things to note: 344 is the message ID. The message is 8 bytes, which is the max payload length of a CAN 2.0 message. The encoding of the 8 bytes is shown bit by bit in the next section. This is literally the decoder ring that converts the raw bits to engineering units. Now, let's take a look at a simple IMU DBC file using 11-bit IDs. First thing to note is we define 3 messages here, one for dynamic tilt, one for accelerometers, and one for angular rate. The messages for attitude, acceleration, and rate must be separated into 3 separate messages because CAN data packets are a maximum of only 8 bytes. We could add a 4th message here for a magnetic field if we wanted to add that output. Now, let's take a look at the code implementing this. So, we will open up the DBC example app posted online. This first file, dbc_file.h, it defines the message IDs that we just looked at in the DBC file. It defines the scaling constants as well as the data structures for the message contents. The dbc_file.c file has the code which takes the floating point sensor values from OpenIMU's core code and then formats them into CAN packets and sends the data out. The file can.c contains the low-level CAN driver code that actually interfaces to the ST micro CPU to actually deliver messages. This file, tasked communication dbc.c, shows the loop, which is really simply a loop here. It simply goes around the loop transmitting data out. Okay, so now that we've got the code, let's go ahead and compile it, and we'll load it on to the OpenIMU with JTAG. Now that we've done that, we can come over here and we can display that on the Raspberry Pi base setup. Now let's consider the J1939 standard, what it's for, and why it's an even better way to share data over the CAN bus. J1939 is an SAE global standard for vehicle sensor data over CAN. It globally defines messages for tilt, acceleration, angular rate, and many other sensor types. If we implement J1939, then everyone knows exactly how your messages are formatted and work. J1939 defines messages with a PGN or parameter group name. Inside the messages are datums. These datums are defined by slots. Slots give the encoding of the datums. PGNs and slots for roll, pitch, acceleration, angular rate are shown here. And J1939 goes beyond just globally defining messages and data according to a standard. It also supports address claim. Address claim lets a unit dynamically claim a unique address on the CAN bus, as there could be multiple of the exact same device on a CAN bus. In the previous example, without this address claim feature and a standard, this would mean that it's not possible to have multiple devices of the same type without actually going in and changing the message IDs of the 2 similar devices. Moreover, ensuring there are no message ID conflicts is purely a manual process with 11-bit IDs. So this is a real benefit of the J1939 standard. J1939 also lets you implement proprietary commands that are not in the standard. For example, proprietary commands could include commands to configure the unit in case the IMU needs to configure the output data rate, or say set the orientation dynamically in the field, or even filter settings. All these things can be added as commands over the CAN bus. What's more is J1939 supports a user in the field being able to move these proprietary command IDs to new IDs in case of a conflict with another device. All very powerful stuff. So, As with the 11-bit DBC example, Asina also provides a complete example application for J1939. Let's take a look at the code implementing the J1939 standard together. All right, so we'll start from SAE_J1939.h file, which defines the messages. Next, we're going to take a look at the actual task communication loop. That's this task communication J1939.c. Before we had a simple loop that just outputs data. Here we have a little bit more complex loop. It outputs periodic messages, but it also looks for incoming messages, address claims, and other features. All right, so let's compile this code and load it onto the OpenIMU 300RI. Now that we've got it compiled, we will go ahead and connect it to the vector tool. Notice how the vector tool can automatically convert these CAN messages into engineering units. It's following the J1939 standard to do that. So in summary, we have investigated the OpenIMU 300RI, which provides an open source CAN-based IMU platform to develop sophisticated applications. I really appreciate you taking the time to listen to this video, and please subscribe to the Asina Developer channel. If you have any questions, feel free to leave them in the comments below.